So far, we learned about the coordinate representation. So if we have a basis and we have a vector like x in vector v, which is written as a linear combination of elements in the basis, we know that we can find the scalar c1, c2, cn that are called the coordinates of vector x with respect to or relative to basis v. And we denote it this way. Now, if you have two bases, b and b prime, for vector space v, and you're trying to find a relation between the coordinate matrix of x relative to b and coordinate matrix of x relative to b prime, we're introducing a new concept, transition matrix. This is going to be a matrix like P such that the coordinate matrix of x relative to b prime is the product between the inverse of that matrix, transition matrix, by the coordinate matrix of x relative to b. So let me give you an example. In this example, question says, find the transition matrix from basis b to basis b prime for the basis of, we're working with a plane, which are given to you as, b is given to us as -3, 2, and the second vector 4 and -2, and b prime is given to us as -1 and 2, and 2 and -2. So we're trying to find that matrix that when we are doing the multiplication, the product, it gives us a relation between these two matrices. So basically, if you have a matrix like a vector like x, it's written as, for example, c1, let's call it v1 and v2, and this guy is called, for example, u1 and u2 for simplicity. c1 v1 plus c2 v2, which is c1 -3 and 2 plus c2 4 and -2. So this guy is equal to -3c1 and 2c1 plus 4c2 and -2c2. So the elements of this vector, for example, a and b, are written as, for example, if say x is equal to vector, including a and b, this guy is equal to -3c1 plus 4c2 and 2c1 minus 2c2. So basically, -3c1 plus 4c2 is a, and 2c1 minus 2c2 is b. As you remember, we can form a matrix, -3, 2, 4, and -2, which is multiplied by c1, c2 gives you a and b. Now we want to know what is that matrix P, that when we are multiplying that by this matrix, it converts it to a new matrix with coordinates of vector x with respect to basis b prime. What we can do here, we can write the coefficients of b prime as well. What do I mean by that? Think about it this way. Here, you are writing x using the elements of basis b. Now write x using the elements of basis b prime. The same process. In this case, x is a and b, which is written as negative d1 plus 2 d2 and 2d1 minus 2 d2. So basically, negative d1 plus 2 d2 is a, and 2d1 minus 2 d2 is b. The same as before. Here you have negative 1, 2, 2 and negative 2 multiplied by d1 and d2 equals to a and b. Instead of writing it this way, you can basically combine the coefficient matrices. So I'm going to erase this part of the board and write them all down here. So since it's transition from B to B prime, you're going to write down the coefficients of B first, negative 3, 4, 2 and negative 2, and the coefficients of B prime, or just the vectors in column form, negative 1, 2, 2 and negative 2. Let's start applying the reduction. If you try to reduce this, you can, for example, divide the very first row by negative 3. You get 1, negative 4 over 3. And here you have a third, negative 2/3. And here you have 2. And just do some algebra and start converting these into the following. 1, 0, 0, 1, and the elements here should be 3, and then 2, negative 2, and negative 1. This guy is basically matrix P. So the transition matrix is 3, negative 2, 2, and negative 1. Again, if you write down the coordinate matrix with respect to B and the coordinate matrix with respect to B prime, this guy is equal to the inverse of the transition matrix by the coordinate matrix relative to B prime. Let me give you an example to clarify. So take a look at this. We are in the plane, am I right? Check. So we're going to do the check so you can understand the analysis behind it. Take a vector like x, 1 and 0 in the plane. Well, 1 and 0 can be written as the combination of elements in B and also B prime. 1 and 0 is equal to C1, negative 3 and 2, plus C2, 4 and negative 2. So basically 1 and 0 is equal to negative 3C1 plus 4C2 and 2C1 minus 2C2. Or basically you are saying that negative 3C1 plus 4C2 is 1. And here 2C1 minus 2C2 is 0. So from the second line, C1 is equal to C2. So if you substitute it here, you get C2 equals to 1, which is basically the same as C1. So this vector 1 and 0 has coordinates 1 and 1 with respect to basis B. 1 and 1. If I multiply this vector by transition matrix, it gives me the coordinates written with respect to elements of B prime. So P, X, and B must be equal to X with respect to B prime. Take a look. Just do the multiplication. I already know what P is. 3, -2, 2, and -1, multiplied by 1 and 1. So just multiplication. 3 times 1 minus 2, 1, 2 times 1 minus 1, 1. So we expect to get this guy, this column matrix, if we find the coordinates of X with respect to B prime. Let us check to see if it's true or not. If I write 1 and 0, it's the same vector. I'm not changing the vector. D1, -1 and 2, plus D2, 2 and -2. This is basically saying that, hey, 1 and 0 is equal to -D1 plus D2 and 2D1 minus 2D2. So basically, we are saying that -D1 plus 2D2 is 1, and 2D1 minus 2D2 is 0. Or basically, D1 is equal to D2, or D1 is equal to D2 equals to 1. So basically, we are saying that, hey, if I find the coefficients of linear combination for vector X with respect to elements of B prime, it must be 1 and 1, which is basically the same here. So this transition matrix helps us to find those coordinates much more easier.